So let's see some image generation approaches with deep neural network. So there's one idea, that we want to generate some kind of input data based on the desired output. So that's kind of the opposite. Usually we have some input, we put it in the network, and we've got some output. But now let's do it the other way around. Let's say that we want some desired output, and we will modify the input to achieve that output. And so that's an interesting idea to kind of shape the kind of input we will use for that neural network. And the approach means here that, let's say that we want to generate an image of a given class. We just said, we say like we want the image to be from that class, and we will do gradient descent, not on the weights of the neural network, but on the value of the input, the X. And so we will do gradient descent on the X in order to generate a new image, for example, or a new data that will provide the desired output, which is computed according to like the obtained and desired output, which you get into the error function here. So we will generate a new data from the initial value of X. So we can just start from an X and modify it until the decision is made the way we wanted it. And the network weights do not change. So this kind of idea has been applied in what has been presented in some time ago in 2015. So it's getting quite old, but that was really interesting at that time. What is like the deep dream thing of Google. And so the idea is that they are like starting from that image, say an image of an horizon here, and they apply this gradient descent on the image to modify it to get as output here towers and pagodas. So they were, and this look like some kind of towers here. So this is the results of gradient descent applied on that image, transform it into that kind of image in order to get the neural network to say, yeah, this is a tower. Likewise, here we have a tree. A tree is in fact here in the image, and we are transforming that image into something where the network will say there is a building, and there is in fact some kind of building. And likewise, we have a leaf here, and we modify this for the class bird and insect. So the neural network was, I would say we obtained this image from the neural network, and we can see this as dreams of the neural network, or the way things can be represented to get it to generate the output we wanted. So this kind of image are a little, I would say, funny to see. They are quite not necessarily natural, but they may look like the things we are looking at with some elements, just modify from the original image into something new that include elements that will tell us, yes, this is some kind of building, and yes, this is some kind of towers and pagodas. So going beyond this, we have also the notion of style transfer, and the idea is that we have an original image and we have some style, and we would like to apply this style here in that content. So we want to preserve the content of the sea turtle, but we want to modify it in the style of that image, which is the well-known Japanese art, which is called the Great Wave of Kanagawa. So basically, we put this into these convolution layers, and we try to produce a new image, which will preserve the content loss. So we will get this image generated, optimized such a way that the content loss is minimized. So the content here and the content there are coherent. Likewise, the style here and the style there are also coherent. So we've got the style loss minimized. So this is a different way of generating an image. This is, in fact, the topic of homework 4, where you will do some style transfer like that way. We also have the generative adversarial networks, the GANs, that we saw in the last module, but we will revisit again because it's kind of important in terms of generative model. This is really an important generative model where we get, I would say, two neural networks that are competing. So we have a discriminative network that is looking to distinguish true data from the problem. So we have real data from the problem, and we have generated data, which are fake data. And the discriminative network try to identify which input is real data and which input is fake. And we have the other network, which is the generative network, that tries to produce fake, and tries to make them as authentic as possible in order to fool the discriminative network. So these two networks are in competition. The generative one try to make good fooling data, and the discriminative try to identify which is right, and which are fake data. And which is great also with that is that we don't need real labels. We are training these networks only based on a data set, and we try to learn to produce other data that are similar to the original data from the data set. An example of that is what we call image-to-image translation. So it is based with conditional GAN. So we give it a little more than just having a training with data sets. We in fact condition the network on some image. For example, here we give it a black and white image as input. So this is the condition, and we want it to produce a new version of it, which is a color image. So the generative network tries to colorize the black and white image in a way that will fool the discriminative network. The discriminative network will not be able to differentiate between real colored images from like colorized images with the generative network. Likewise, here we convert an input which is a day image to a night image, which is the same environments but in night. I'll try to move like from aerial photos to map photos with this kind of model. So this is just an example, but that is based on GANs, which are really important milestones in terms of generative models. And the model is working that way. So we really have a discriminative network and a generative network. These two networks are in competition, and we have a real data set. So we give data from the real data sets or the generated data, which are given there. And then we just try, so we are in a binary classification setting where we try to figure out which is real, which is fake. And then I would say we've got some loss over that, and that is used to train the discriminative network. But we also train the generative network from that same loss that went through all the discriminative network. But now we are inverting that. So we try to maximize that loss in the sense that we want to get the discriminative network to be as poor as possible to backpropagation from the output through the discriminative network through the generative network. So the point with GANs is that it's really a key approach for the development of generative model. So I would say more historical generative model are based on GAN. You know, the one before 2020 were basically GANs, most of them. For example, this person does not exist is based on style GAN, which is another GAN which is able to evaluate the style of a picture. What is great with GANs is this based on self-supervised training. So we don't need labeled data or explicit quality metrics. We just need a data set, and we are able to train with supervised signal models without having labels. So that's kind of an interesting approach that is working quite well when we are able to set up our problem to be trained in a self-supervised way. However, we don't get any guarantees of the realism or the quality of the data. You know, the GAN is based on a competition, and it may fail, and the discriminative network may accept, may be fooled by some data that are for the human eyes easy to detect as fake. So we don't have any kind of guarantee on that, but still, you know, it's kind of effective for different cases. It is relatively complex to train. It's not an easy model because we need to train to make a trade-off between training the generative and the discriminative model. And the discriminative task is easier than the generative task. It's quite easier to detect fake, and it's much harder to make fakes. So this difference make it more complex to train. And also we see something that we call mode collapse, where the coverage of different things is lost, basically tends to generate always the same kind of image or the same kind of objects, because this is the objects that may be fooling the discriminative network, and it doesn't learn to generate, I would say, rarer cases that are present in our training set, in our data set, but that is not, I would say, necessarily reproduced with the generative model, because the generative model just try to fool the discriminative network, doesn't try to generate every possible cases that we see in the data set. And the training of that can be quite computationally intensive. You know, this kind of competition with two networks with kind of loss going through the discriminative network and then through the generative network can be quite computationally intensive. So that's not necessarily, I would say, that's not a cheap way to get a generative model, even though it's kind of manageable. We can still train GANs on single GPUs.